everyone. Myself, Dr. Ranjith Kumar Gatla. I am working as an associate professor in Electrical and Electronics Engineering Department, IARE. In today, we are going to discuss about the single phase bridge converters. In the previous class, we have already discussed the single phase midpoint converter. In that, the full bridge and off bridge both we have discussed. And in today's class, there is another type of converter, which is the bridge type of converter, that we are going to discuss in today's class. Again, here also in the single phase bridge converters, there are two different types of converters. One is the single phase full bridge converter, and the second one is the single phase half bridge converter. And again, in the single phase full bridge converter, similar like the other converters, similarly here with R load, RL load as well as RLE load is there. So one by one we will discuss in today's class. Here first we are going to discuss about the single phase full bridge converter with R load. Here when coming to the configuration, the circuit diagram, here this is the full bridge rectifier circuit. This is a single phase. So here the total number of thyristors are 4 thyristors, and the two legs are there here. The two legs are connected in parallel with the load, and here each leg consisting of 2 thyristors, and those 2 thyristors are connected in series. And before going to discuss about the operation of the single phase bridge converter, so let me tell you some condition that we must consider to discuss the operation of the single phase full bridge converter. So the first condition is, here as we can see, in every leg there are 2 thyristors which are connected in series. Okay, the 2 thyristors must not turn on at the same time, or the 2 thyristors should not conduct at the same time. That is the first condition, because as we can see here, let me consider if the T1 and T4 are conduct at the same time, then there will be a short circuit applied across the load, so that the load may get damaged, so that the high current flow through the load and the load may get damaged. So to avoid that, the 2 thyristors in the same leg, or the 2 switches in the same leg, should not conduct at same time. So which means when the thyristor T1 is turned on, or in the turn on position or in the conduction position, then the thyristor T4 must be turned off. And similarly in the second leg also, if T3 is turned on, then T2 must be in the turn off position. And if T2 is turn on position, then T3 must be in turn on position. Okay. So, and one more thing, in each leg at a time only one thyristor must be turned on, which means suppose, and another thing here we can make it as, here there are the upper 2 switches are there and lower 2 switches are there, right? So in let me consider here, this is the positive group and this is the negative group of thyristors. So in each case, one thyristor from the positive group and another thyristor from the negative group must be turned on. Of course, there are here the 2 different cases are there, okay, or 2 different modes are there. So in the first mode, one thyristor from the positive group and another thyristor from the negative group will turn it on. So which means, let me consider here, if T1 is turned on, then the T2 must be turned on, because here the T1 is from the positive group. Anyway, 2 thyristors from the same group will not turn on. So that's why one thyristor, it is T1, and another condition is T1, T4 should not turn on at the same time, or should not conduct at the same time. So which means only the possibility is T2. Similarly, if T3 is turned on, okay, then we must take T4, another thyristor, that is T4 from the negative group. Like that, these are some conditions. Okay, so based on these conditions, we are going to discuss about the operation of this single phase full bridge converter. So here, before coming to the operation, first here the input is the DC supply and output we will get the AC. So for that here, input is the AC supply and the output we will get as a DC. So for that here, initially we have given some DC supply some AC supply to the input side. Okay, and initially when the thyristor T1 and by giving the gate signal, okay, the thyristor T1 and T2 are turned on. So when the thyristor T1 and T2 are turned on, then the load current will flow from here the positive terminal to this T1 to this load R2 and T2 to and the negative terminal of the supply. So which means here in case 1, the load current will flow from Vs positive terminal to T1 to R to T2 to the Vs negative terminal. Because let me draw here the waveforms also. In the waveforms, here the input is a sine wave. Like this. Okay. Then here these are the gate signals. Let me consider, because at the same time T1 and T2 are triggering. So IG1 comma G2, and the another gate signal here just I am writing are IG3 and comma 4. So of course initially when the positive cycle is applied across the circuit, then the forward biased voltage applied across the T1 and T2, so that the the thyristor T1 T2 get into the forward blocking mode. Okay, forward blocking mode. When let me consider here alpha is equal to, let me consider here for alpha is equal to 30 degrees, or alpha 1 is equal to 30 degrees. So we are giving the gate signal at 30 degrees. Okay, then the thyristor T1 T2 will get turned on at the 30 degrees. So here let me consider here, this is the alpha T1 and this is the output voltage V0, and then here as we can see, of course this we will discuss later. Here at this particular point, then this is pi. Then here the V0 you will get like this, that is the V0. So here let me consider alpha is equal to for the 30 degrees. So at this point we have triggered T1 and T2. So then the output voltage will follow the input supply voltage, then you will get like this. Then after that immediately here the supply is get reverse biased. So because of the natural commutation, the thyristor T1 and T2 will get turned off. Then at this point the T1 T2 will get turned off. Then again the forward, then because of the reverse biased because of the negative cycle, here the forward biased applied across the thyristor T3 and T4, then the thyristor at this particular point the T1 T2 are get turned off and the T3 T4 are get into the forward blocking mode. Then when we will give the gate signals to the T3 and T4, then at that particular point the T3 and T4 will get turned off. So at pi plus alpha, this is alpha, and at pi plus alpha we are giving the gate signal to the thyristor T3 and T4. So this is pi plus alpha. Then at this particular point the thyristor T3 and T4 will get turned on. Then here again you will get the positive voltage. Similarly this cycle will continue. Then after again after 2 pi, here because of the natural commutation the thyristor T3 T4 will get turned off because the reverse bias applied across the T3 and T4, and at the same time the forward bias applied across the T1 and T2, then again the T1 T2 the thyristors will get into the forward blocking mode. Then when you are giving the gate signal to the T1 and T2, then the T1 T2 will get starts conducting, so that again you will get the output voltage as a positive. So this is how the operation of the single phase full bridge converter. And the same circuit, like in the second case, case 2, here that is the Vs negative to, in the second case, which is from Vs negative to Vs negative to T3 to low to T4 to the positive terminal, which means from B2. Okay, so here T2, T3 to low to T4 to Vs positive. This is the flow of, the path of the load current. Okay, in this case, both the current and voltage are positive. So again, the current, because this is the R load, so the current is also same like in the voltage waveform it will follow. So here I will show you the other waveforms also in this case. Here, yeah, here you can see at this particular point, of course, when VAB which is applied, okay, the positive cycle is applied, the T1, T2 will get into the forward blocking mode. So after giving the gate signal at alpha is equal to alpha is equal to 30 degrees, let me consider, then the load current, the voltage, the T1, T2 will get into the conduction mode, so that the load current will flow from the Vs positive to T1 to load to T2 to the negative terminal. So that's why here you are getting this the positive voltage. So this is the positive voltage that you will get. Then similarly the load current also. So which means here T1, T2 will get conduct, and here T2, sorry, T3, T4 will get conduct, then again T1, T2 and T3, T4. Like this, the thyristors will get conduct in different periods. So when coming to the gate terminals, anyway here, because I have taken the gate voltage VT1, VT2 and VT3, VT4, because as we discussed, T1, T2 will turn on at the same time and also the turn off at the same time. So which means it will conduct the same duration. Or whatever the duration the thyristor T1 will conduct, the same duration the thyristor T2 will also get conduct. So that's why here I have taken the terminal voltage of VT1 and VT2 are same. So that's why instead of 2, I have just considered as a VT1 and VT2. Yes. So how long the T1 and T2 are here conducting? Only this period. Okay. Only this period the T1 and T2 are conducting. So then, which means here, this period the T1 and T2 are turned off. So that's why here we will get the terminal voltage of this one. Right. And after that here, okay, anyway, in this case also, what is that the T1, here also the T1 and T2 are turned off. Okay, that's why here it is following the same as the supply voltage up to here. Then again here T1, T2 are conducting. So when it is conducting, the voltage across this is 0. Then again here, from here it is not conducting, then again here it is following the input voltage. So this is how we can draw the the voltage across the thyristor T1 and thyristor T2. Similarly, when coming to the voltage across the thyristor T3 and T4, just the reverse of the T1 and T2, because as we know, when the T1 and T2 are turned on, the T3 and T4 will be turned off, and when T3 and T4 are turned on, T1, T2 must be turned off, right? So at the same time, it is not possible to turn on all the thyristors. So that's why here you can see, here there is a voltage, okay, the terminal voltage across the VT1, VT2, because these two are in the turn off position. So which means at this particular moment, the T3 and T4 should be turn on. So that's why here during the turn on, the voltage is 0. And in this case, as you can see, during this time, again T1, T2 are turned off. Because of that here, which means here T1, T2 are turned on. So which means T3 and T4 should be turned off. So that's why here it is following the minus Vm. Right? And again here, because the reverse biased voltage applied here, because this is the forward biased voltage, So at the same time, for the T3 and T4, it will be reverse biased voltage like that. Here, this one. So that's why here we are getting the negative voltage. Then again, at this particular moment, again still T1, T2 are what is that, not turned off immediately. Okay, so that's why here you are getting some voltage. Then after that, again here T3, T4 are turned on because the T1, T2 are turn off. So that's why T3, T4 are turned on. So again here the 0. So like this, we can also draw the what is that, the thyristor terminal voltages. The thyristor terminal voltages, right? Then for this, and next case is for the RL load. Of course, R load is very simple, and similarly, we are going to discuss about the RL load. Here, RL load is what is that? This is very important for the RL load. Okay, so in this case also the operation is more or less same, because there are two modes of operation in the first, because here as we know, the input we are giving is the AC supply, so it contains positive and negative cycles. So during the positive cycle, what is that, the forward biased voltage applied across T1 and T2. Similarly, in during this positive cycle, because the negative voltage, this will apply across the T3 and T4. So that's why, because of the reverse bias applied across T3 and T4 will not to get turn on, only T1 and T2 will get turn on. And similarly in the second case here, this is the forward biased voltage, which means the across the T3 and T4 will get forward biased voltage. At the same time, the reverse biased voltage applied across the T1 and T2. So that's why due to the natural commutation, the T1 and T2 will get into the turn off position. Here also same thing. But here, because of the nature of the load, a small amount of negative voltage also we will get. A small amount of negative voltage also we will get. That depends on again the firing angle. Because as we can see, the single phase full bridge converter with what is that, RL load is a two quadrant chopper. The two quadrant chopper. So how a two quadrant chopper means, here based on the firing angle alpha value, okay, the voltage can be varied from what is that, plus VDC to minus VDC. Varied from plus VDC to minus VDC. So that's why here, as you can see, for particular range of alpha value, here the output voltage and current is always positive, but for a particular range of alpha value, the output voltage may be negative. So that's why here, as we can see, it is a two quadrant operation. I mean, it can be operate in the two quadrants. Yes. When coming to the operation of this one, here again, first initially, because of the positive cycle, the forward biased voltage applied across the thyristor T1 and T2. Then the thyristor T1 and T2 will get into the forward blocking mode. And let me consider here, yes, here this is not the case. Yeah, this is the case. Yeah. For the first one here, let me consider here alpha is equal to 60 degrees. Okay, which, because here we are going to discuss in two different modes. Okay, one is alpha is less than 90 degrees, and another one alpha 1. Okay, and then alpha is greater than 90 degrees. Okay, so if alpha is less than degrees, what is the total average output voltage, and if alpha is greater than 90, what is the total average output voltage? So that we will discuss. Right. So in the first case, we have considered for the alpha value, firing angle is equal to 60 degrees. For the firing angle 60 degrees anyway, even though the forward biased voltage applied, until you give the gate signal to the thyristor will not get into the conduction. At alpha is equal to 60, we are giving the gate signals to the thyristor T1 and T2. Then the thyristor T1 and T2 will get into the conduction mode. So here, this is how the T1 and T2 will get into the conduction mode up to pi degrees. Let me consider. Okay, so after pi degrees, the reverse biased voltage applied across the T1 and T2, and at the same time the forward biased voltage applied across the T3 and T4. So before case, when we are considering the simply R load, that time immediately T1, T2 will get into the turn off position. But here, because of these inductance, okay, a small reverse biased voltage will also flow through the thyristor T1 and T2. So that's why here you can see a small reverse biased voltage is flowing across, through the thyristor T1 and T2. Then when the thyristor T1 and T2 will get into the turn off, because next when the thyristor T3 and T4 are turned on, because at pi plus alpha, again at this particular point at pi plus alpha, okay, again we are giving the gate signals to the thyristor T3 and T4. Then immediately the thyristor T3 and T4 will get into the conduction. At the same time, the thyristor T1 and T2 get turned off. Right? Because as we know, the condition to get turn off the thyristor, not to just apply the reverse biased voltage. So we are applied some amount of the reverse biased voltage to get the anode current below the holding current. Then only the thyristors will get into the turn off. Which means up to this point, okay, the anode current is not below the holding current. That's why these thyristors are still conducting in the reverse biased also. But when the thyristor T3 and T4 are turned on, so immediately the latching, the holding current, the anode current will get down below the holding current, so that the thyristor T1 and T2 will turn it off. Okay, so that's why here the thyristor T1 and T2 will get turned off. Okay, at this point again the thyristor T3, T4 are turned on, then again the voltage that you will get as a positive voltage. Then again at 2 pi, okay, the the reverse biased voltage applied across the T3 and T4, and the forward biased voltage applied across the T1 and T2. Okay, but even though reverse biased voltage across the T3 and T4, the T3 and T4 will not get into the turn off position because of again the inductance effect. Okay, so that's why a small amount of the voltage will flow in the reverse biased through T3 and T4. Okay, then when at 2 pi plus alpha, again we will trigger T1 and T2 and we will give the gate signals to the T1 and T2. Then T1, T2 will get turned on. Then again here at the same time the T3 and T4 will get turned off. So this cycle will continue so that you will get the output voltage waveform. And one more condition here that we are considering is again here the load current waveform depends on the value of the inductance. So let me consider here for high inductance value, let us consider here the load current is constant. So that's why here the load current we are making as a constant load current. Then when coming to the, as you can see here, for simply from the waveform itself we can say here if you take the time period of this particular waveform is pi from here to here. Okay, so in this particular time period, okay, if you find the average value of this waveform, because the positive portion of the waveform is higher than the negative portion, so the average voltage value is positive. So which means the V0 is positive. So then suppose if you take alpha is equal to 90 degrees, then you will get the the negative portion and the positive portion are same, so that you will get the V0 is equal to 0. And if you take alpha is greater than 90, then the negative portion is higher than the positive portion, so that you will get V0 is equal to negative. So which means here anyway it is a 2 quadrant rectifier. Okay, so here it is V0, negative V0 and positive V0, and this is the I0. So the current is always positive, but the voltage is varying from minus V0 to from here to here, which means from here 0 less than alpha less than 90 degrees it is positive, and here this is 90 less than alpha, 90 greater than alpha less than 180. Okay, so here it is in between 90 and 180, here it is the negative output voltage. Similarly, the same thing we will discuss for the alpha is equal to 135 degrees. So for alpha is equal to 135 degrees means at this particular point we are giving the gate pulses to the thyristor T1 and T2, so that the thyristor T1 and T2 will get turned on. So that then here this is the output voltage waveform. But even though here the reverse biased applied voltage applied across the T1 and T2 and the forward biased voltage applied across the T3 and T4, the T1 T2 will not get into the turn off immediately, and the T3 T4 also will not get turn on immediately. So until unless when we give the triggering pulses to the T3 and T4, okay, so at that particular point T3 and T4 will get into the turn on, and T2 and T1, T1 and T2 will get into the turn off position. Until that it will conduct in the reverse biased. Right. Then similarly again, what is that? The output current is same here also, because as we just consider the high value of the inductance, because of that we will get the constant output voltage. Okay. Then what is that? The thyristor currents and the thyristor voltages that we know already. Okay. When the thyristors are T1, T2, how long it is conducting from what is that? Alpha to alpha plus pi plus alpha. Okay. So because here from here to here it is conducting, so that's why we are getting the thyristor currents, and from here to here it is turned off. The thyristor T1 and T2 are turned off. That's why there is no current, and the vice versa will happen in the the reverse case happen in the T3 and T4. So which means when the T1 and T2 are turned on, turn off position, then T3 T4 will turn on. So that's why here the current. So which means here T1, sorry. So here T1, T2 will get turn on, and here T3 and T4 will get turn on. Like this, the T3 and T4. Okay, and the same thing we can also verify with the mathematical equations. Like here, you can see, as we know, the average load equation, that is EDC is equal to, or in general notation, as we know, we have already discussed in the previous classes, that is V average, which is equal to 1 by T into integral 0 to T Vm sine omega T into d omega T. Okay, so here again from this waveform we have to identify the total time period as well as the conduction period. Here the total time period is pi simply, that we can easily identify, and the conduction period is, here it is alpha to pi plus alpha, because from here to here it is conducting. Okay, alpha to pi plus alpha Vm sine omega T into d omega T. Then we just apply the integral 1 by pi into, here let me consider Vm by pi into here minus cos omega T with the limits of alpha to pi plus alpha, and if you substitute these limits and simplify, then we can get the average voltage equation. Okay, so for that here already it is derived. Okay, so like you can see, EDC is equal to 1 by pi. EDC is equal to 1 by pi into integral alpha to pi plus alpha Em sin omega T into d omega T. Then here 1 by pi into Em sin omega T, the integral of sin omega T is minus cos omega T, and the limits are alpha to pi plus alpha. Then if you substitute these limits, so here because of cos alpha, okay, instead of pi plus alpha, here I have, again I have multiplied with minus, so that cos alpha minus cos pi plus alpha. So here cos pi plus alpha is nothing but again minus cos alpha. So that cos alpha plus cos alpha, here you will get the 2 cos alpha. Then EDC is equal to 2 Em by pi into cos alpha. This is the average value, right? Then from this also you can just identify. Okay, suppose here I am considering the 3 different values. First let me consider alpha is equal to 30 degrees, or just whatever we have considered, that we can consider alpha is equal to 60 degrees, and alpha is equal to 90 degrees, and alpha is equal to 135 degrees, that we have considered just now. So if you substitute alpha is equal to 60 degrees, okay, in this equation, then the value of these cos alpha will be positive. Okay, And similarly, and we can easily say the cos alpha value is positive for 0 to, again what is that, for 0 greater than alpha less than 90 degrees. Okay, so during this condition the cos alpha value is positive. So if the cos alpha value is positive, then the total EDC value is positive. And alpha at alpha, I mean cos alpha is 0, okay, when alpha is equal to 90 degrees. Cos 90 is 0. Then the total EDC value will become 0. And when cos alpha value is negative, okay, when is greater than alpha, I mean 90 greater than alpha less than 180 degrees. So that's why here if you take the quadrants, here this is, let me consider I naught, and this is V naught, and this is minus V naught or E naught. Okay, so here we can operate the full bridge converter in these quadrants. Okay, then you must consider the alpha value in between 90 degrees. And if you want to operate the same full bridge converter in this quadrant, then you must consider the alpha value in between 90 and 180 degrees. Okay, so which means when you are considering alpha value is greater than this thing, okay, the load will supply to the source. The load will supply to the source. So of course here this is the EDC, and again ID EDC by R, then you will get ID is equal to 2 EM by pi into 2 EM by pi R into cos alpha. Similarly, we can also derive the RMS value, but anyway, we have already discussed how to derive the RMS value. So for that, the RMS V RMS, which is equal to 1 by T into, again integral 0 to T V M square into sine square omega T into d omega T whole to the power of 1 by 2. Whole to the power of 1 by 2. So by simplifying this equation, again we can find V RMS. Here again T is pi, okay, and 0 to 2 is again alpha to pi plus alpha, the conduction period of the waveform, right? Then here the same thing I have written here, you can just see during the interval of alpha to pi, both supply voltage and the supply current are positive. Therefore, the power flows from AC to DC, which means this full bridge converter can be operate in the two different types of modes. One is the rectifying mode, another one is the inverting mode. So the rectifying mode is nothing but AC to DC, and the inverting mode is nothing but DC to AC. Right. So when the full bridge converter will be acting as a rectifying mode, when the alpha value is in between, what is that, 0 to pi. The alpha value is in between 0 to pi. Then both the supply voltage and supply current will be get positive. Therefore, the power flows from AC to DC, because here we are considering the positive power when I and V both are positive. Then that, because as we know P is equal to V into I, then the total power is positive. So positive is nothing but from AC to DC. And from pi to pi plus alpha, voltage negative but the current is positive, then the load returns some energy to the supply system, but the power flow is from AC to DC only. From pi to pi plus alpha. Similarly, in the inverting mode, okay, if the firing angle is greater than 90 degrees, then the DC terminal voltage waveform contains some negative component of the fundamental components of the AC line. So that's why here the negative power, which means, I mean, the positive and negative power is nothing but the direction only. Okay, so suppose if you take here, this is some simply converter. Here this is AC and this is DC. Okay, if you consider the power direction from this point to this point is a positive, then if the negative power is nothing but the opposite direction from DC to AC. So if a converter that can convert the DC to AC means inverter. So that's why it is a inverting mode. So the full bridge converter can operate in the rectify mode as well as the inverter mode. And that is based on the firing angle that we are considering. If you consider the firing angle less than 90 degrees, then it will acting in a rectifier mode. And if you consider the firing angle it is greater than 90 degrees, then it will act as a inverter mode. Right. So this is one of the added advantage of the full bridge converter when compared to the half bridge converter. Right. Then we will discuss about the single phase half controlled bridge rectifier. And we have already know why we are considering this is a half controlled and full controlled. Okay. So which means here why we are this, I mean you can just compare the two circuits. Okay, just now we have discussed the full controlled bridge converter. So full controlled means all the switches are controllable. All the switches are the controllable. But you can see in half control, only half of the switches are controlled and another half of the switches are uncontrolled switches. As we know here, of course, not full, but anyway, some extent we can control the semi-controlled switches T1 and T2. But D1 and D2 are uncontrolled. So that's why here this is a half controlled bridge rectifier. And in half controlled bridge rectifier, but the major difference between the full controlled and half controlled bridge rectifier is, okay, because here, of course, anyway, the thyristor will also not allow the reverse biased voltage, but up to some extent it will allow, okay, but fully it will not allow. But the diode, at no point it will allow the reverse biased voltage. So which means here the single phase half control bridge rectifier, this is again a single quadrant converter. Okay, the half control rectifier is a single quadrant converter, which means for any value of the alpha which is in between 0 and 180, always the old output voltage and current are the positive. Okay, so here then suppose let me explain the operation of this single phase of controlled bridge rectifier. Okay, same like in case of the full bridge rectifier. So in the first case, again here let me draw this one, right? So during the positive off cycle, the forward biased voltage applied across the T1 and D1. So the T1 will get into the forward conduction mode, and after pi degrees we are triggering the thyristor T1, which means we are giving the gate signal after some firing angle. Let me consider which is alpha. Then T1 is turned off. Then the load current will flow this from T1 to this R2 D1 to N. D1 to N. Then you will get whatever the input supply that you have applied, the same voltage you will get across the output. Then which means here at alpha, so here T1 and D1 will get turned on. Similarly, after pi degrees, okay, the reverse biased voltage applied across the T1 and D1, and similarly the forward biased voltage applied across the T2 and D2. Then the T1 and the thyristor T1 will get turned off immediately, and the thyristor D1 also will get turned. Of course, anyway, the diode D1 will not allow the reverse biased voltage. Okay. Then again after pi plus alpha, we are giving the triggering pulse or gate pulse to the thyristor T2. Then the thyristor T2 will get turned on. So when the thyristor T2 is turned on, then here the supply voltage, the load current will flow from this T2 to load to D1 to the supply. Which means here again you will get the same like the supply voltage. So here T2 and D2 will get turned on. Like this, the cycle, it is going on. Right. So here you can see the waveforms for this half controlled or semi-controlled. We can also call it as the semi-controlled bridge rectifier. Okay. So here these are the output voltage waveform. As we can see here, when here the T1 is triggered, then you will get this one. Okay, and after that here I mean at pi degrees the T1 will get turned off, T1 D1, then immediately the forward biased voltage applied across the T2 and D2, but after pi plus alpha only we are giving the gate signal to the T2, so that's why at this particular point and again the T2 will get turned on, so that again you will get the positive voltage. So there is no point of negative voltage here. Anyway, if you are using the inductor also, if you are using the RL load also. Okay, so that's how here as we can see here T1 D1 will turn on. Okay, so like that here it will happen. And similarly the gate what is that, the terminal voltage of the T1 and T2, when the T1 is turned on at that particular moment, what is that, the voltage across the thyristor T1 is 0, but in all other the other time the voltage across the thyristor T1 will get, that is same as the supply voltage. And in this case also the average load voltage and average load current that you can see here simply. Okay, so which means here the EDC is equal to Em by pi into 1 plus alpha. So for any value of the alpha value here, this total term will always get positive. Always get positive. So that's why here the EDC is always positive for 0 greater than alpha less than 180 degrees. So that's why it is a single quadrant converter. Single quadrant converter. So the difference between the full bridge converter and the half bridge converter that you can see here, this is full and this is half, and when coming to the EDC equation, EDC, a full bridge converter is 2Em by pi into cos alpha, and in case of half bridge converter here it is Em by pi into 1 plus cos alpha. Okay, Em by pi into 1 plus cos alpha. This is EDC. Then similarly we can find the RMS load voltage also. Already we have discussed these things in when we were discussing about the basic full bridge and half bridge converters. Okay, the equations are same, whether it is a what is that, the midpoint converter or the bridge converter, or a simply what is that, because in full bridge also we have just what is that discussed by taking simply two thyristors. Okay, in that case we have already derived the average and RMS value equation. So here also we are the same equations here we have derived. So here we RMS is equal to this one for this half bridge converter. Okay, and the ERMS will get the maximum when alpha is equal to 0, because when alpha is equal to 0 it will utilize, the thyristor will utilize full of its period. Okay, so this is how this is all about the bridge converters. Okay, in the next class I will discuss the other topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.